This is tutorial 2 of chapter 2 of the digital soil mineralogy with R course. And in this tutorial, we're going to be looking at doing quantitative phase analysis using full pattern summation functions in R. And that is applied to X-ray powder diffraction data. And the best way to describe and explain how this full pattern summation approach to quantification of phases from diffraction data works is to just go through some examples using the data that's included with PowDAR. And specifically, this uses the RockJock library that was introduced in the previous tutorial in combination with synthetic mixtures that were created to supplement the RockJock library as well. And they are also present within the PowDAR package. So we're going to continue from where we left off. We've got RockJock already loaded in R, but if you don't already have that in place, just load the PowDAR package first, and then load RockJock using data RockJock. So we are going to use the RockJock library in a quantification in a moment, and we're going to quantify a sample that's present within RockJock mixtures. So we need to just load this data, which again is loaded from PowDAR. And if we view that, we can see that it is a multi-XY object, which was covered in chapter 1, which is essentially a list of 8 different diffraction patterns, and each of them is a data frame, essentially an XY data frame of the 2 theta axis and the counts axis. And these mixtures have varying compositions. They're carefully prepared, pre-weighed mixtures that can just be used to test out the functions that we're going to be using. And you can get more information on it using the standard form of the question mark before the function name. And this describes what these RockJock mixtures data are. In addition, it actually defines the reference minerals or phases that were used to create them, and they all have corresponding reference patterns within the RockJock library. Further to that, you're also able to access a table of the known weights of these mixtures, just for convenience, so we can see how there are about 8 different phases that can be encountered across the 8 mixtures. They are all prepared with 20 weight percent corundum as the internal standard, but contain various proportions of quartz, K-feldspar, plagioclase, kaolinite, smectite, and illite. In the first example, we're going to quantify mix 1. That's the aim. And again, this is using the full pattern summation approach, and in PowDAR, that's implemented in FPS, the function. Now, if you look at the documentation for FPS, you'll see that it accepts quite a large range of different arguments. But most of them either are optional or have predefined values. So you can get away with only defining a few, sometimes even just 4. Here we're going to define 7 of the arguments. We're going to always start with lib, which is the library, and that's our RockJock reference library with 168 reference patterns that we looked at in the previous tutorial. The next thing to define is the sample. So obviously for quantification, you need a library and a sample to actually quantify. And we're going to quantify mix 1 here from that RockJock mixtures data. The next part is the refs argument, which allows you to define what reference patterns to use in the fitting process. Now, if you could use all 168 reference patterns from RockJock, but it would take days to compute, and you probably won't get very meaningful results from it. So in a lot of cases, it's really useful to restrict the library in some way. Because we already know the composition of this sample, we can easily do that. So in this combined string, C C stands for combine, so we're combining these 6 values in this string. You're able to define phase IDs from RockJock and also phase names as well. So any combination of these. So if we look at RockJock and the phases data frame within it, you can see that there is a phase ID column which contains a unique ID for every reference pattern, whereas the phase name um, can can have multiple values associated um, with it for various reference pattern IDs. For instance, plagioclase has 8 different pure reference patterns, each of them having a unique phase ID. And what that means is if we define something like plagioclase there in this ref string, it will actually be selecting all 8 plagioclase reference patterns instead of having to define their phase IDs 8 times. The remaining values I've put here are all phase IDs. The next argument that we'll define is STD, which is the internal standard, and this needs to be a phase ID of that internal standard. And ideally, there would only be one reference pattern for that standard in the library. We can then define the concentration of it in weight%, and we can also optionally define whether to omit its concentration in the output. So it will omit the 20% corundum in this case and recompute all the values accordingly so that you get what the sample composition is without that additional 20%. So, and then the last thing we're going to do is set the align argument to 0.3, and this defines the extent to which either positively or negatively the sample can shift by on the 2 theta axis in order to get it to align to the what we've defined as the internal standard. So it will shift the observed pattern in order to get it to align to the pure corundum pattern that's in the reference library. So those 7 arguments are what we'll use for this first example. So if we run that, the function talks you through the various stages that it goes through to do the quantification. The first step is actually that alignment, which is really important. So in this case, it's shifting the sample pattern in order to get it to align to the pure corundum pattern that's in the library. And then because during that alignment, the sample ends up on a slightly different 2 theta scale to what it was originally on, it then interpolates the library onto the same scale as that altered sample. It then goes on to optimize, and that is optimizing scaling coefficients for each of the reference patterns that are then used to model the observed pattern. And then it will continue to do that until there are no negative coefficients remaining, because they shouldn't really exist in using this approach. And then once that's achieved, it will compute the phase concentrations. And that's done using the scaling coefficients, so the extent to which each reference pattern is scaled by before it's summed to produce the model fit. And it will combine that with reference intensity ratios, which are provided within the reference library in order to do the quantification, to turn those scaling coefficients into actual mineral concentrations. So then we end up with something called fit1, which is called a powder FPS object. And if you go down into the help documentation in FPS, you can see the various definitions of this object and the items within it. If we just summarize it, we can see that the first 4 items, or first 4 variables within this item are all vectors, and they include the 2 theta axis, the fitted count intensities, the measured count intensities, and the residuals, so the difference between the measured and the fitted. After those 4, there's a data frame called phases. If we look at this, we can see that we have a data frame of 7 rows in this case, and this includes all of the reference patterns that were present or are present in the derived fit. So there may have been others supplied to the algorithm, but they could have been omitted from the process if they were optimized as having a negative coefficient. So we're left with these 7 different reference patterns. And notice how in the 4th column we've got the phase percentage, so the quantified concentration. And because we set the omit standard argument to true, this has been set to Na and all of the other concentrations adjusted accordingly. In addition to this, we've got phases grouped in this pow.fps object, so we can have a look at that. And this is a simplified form of that output that we've seen above. So it basically summarizes the percentages based on the phase name column, and it will sum any values within this column where there are multiple values. For example, plagioclase here, there are 2 reference patterns that are plagioclases, and they are summed to produce a grouped summary here. So this essentially simplifies the output and is a really useful way of finally getting a useful output. And when doing quantification with an internal standard in this way, you don't actually have to quantify all of the sample, all of the phases within a given sample. And due to that, it doesn't necessarily, your results won't necessarily sum to 100%. In this case, they're close to 100% because we've tried to quantify everything that we know is in the sample. Now we defined RockJock, the corundum reference pattern in RockJock, as the internal standard in the previous example, but you could theoretically define anything as the internal standard. So if we look at the RockJock weights data again, we can see that mix 5 is prepared with 20 weight percent corundum, and you could run that the same code as we did before, but define quartz as the internal standard instead for mix 5. Keep its concentration as 20%, omit as true, and align as 0.3. So in this case, quartz will be used for the alignment as well, and it will be used as the internal standard for the computation of the phase concentrations using reference intensity ratios. And again, if you're going to do this, make sure that, or try and make sure that whatever you define as the internal standard only has one reference pattern associated with it in the library. So if we run that, again, it'll take a few seconds to run and talk you through what it's actually doing. But once it's complete, you'll get the full pattern summation complete message, and then you can look at the results again. So here in this case, we've got a few more plagioclases that have come into the fit for mix 5. And again, if you sum the total values, it wouldn't necessarily sum to 100%. Then we can also apply slight transformations to the data from full pattern summation. So for example, if you wanted to actually close the quantitative data so that they did sum to 100%, you can use the close quant function, which can be applied to pow.fps objects, and then that will result in your phase concentration summing to 100%. Now, the examples that we've looked at so far are for samples that are prepared with a known concentration of an internal standard, but some laboratories don't do that because it's an additional step in sample preparation, and it can actually dilute the sample. Well, it does dilute the sample and therefore increase the limits of detection. So in some cases, you may be dealing with samples that don't have an internal standard of known concentration, and you can still apply quantitative analysis to these kind of samples, but you have to assume that you're able to quantify everything within the sample and that it does sum to 100%. So this fit 3 will be an example where we don't know the internal standard concentration. And you can see we move down to defining just 5 arguments here. We still actually define the standard, and that's because we still need to do that alignment step. So in this case, when you don't define the concentration of the internal standard, you'll just be defining something to do the alignment. So we can stick with corundum here, but you could equally choose quartz or some kind of mineral with an invariant chemical composition and a crystal structure and good peaks to do the alignment with. So if we run this, again, it will talk you through the various steps that it goes through to do the quantification. And again, we eventually get the full pattern summation complete message. And now if we look at the phases data frame, we can see that we'll get the full composition. So in this case, we haven't defined corundum, the concentration of it, or said that we should omit that concentration. So we get an estimate of its concentration at around 20%, as would be expected. And if you sum all the phases here, again, it would sum to 100%. So there are 2 different approaches there to doing the quantitative analysis, one with an internal standard of known concentration and one without. And implicit within either approach, there is quite a useful feature in PowDAR, which means that you don't necessarily have to have your sample data and the library data on exactly the same 2 theta scale. So they might be on slightly different resolutions, or one might have a slightly lower 2 theta range than the other. And PowDAR will work with this no problem. So just to show this, how this works, so we can just create a slightly shortened version of mix 1 using the subset function. So we're just going to select data greater than 10 but less than 55 degrees 2 theta, which shortens the data substantially compared to what it was. And then this next line of code simply reduces the resolution by just selecting all the odd rows within that data frame. So we halve the resolution. And if we then apply the full pattern summation, just like we have done in the previous examples, you'll see that it works seamlessly, and you just get an extra message at the start saying that it's harmonizing the library onto the same 2 theta resolution as the sample. And what it's doing there is it's basically firstly working out the overlapping 2 theta range of the sample and the library, and then it will interpolate onto the coarsest resolution, and it will work through until it's completed. And again, you'll get an output at the end of it. So that summarizes just the basics of doing full pattern summation in R. If we just finish by having a look at the final pieces of PowDAR FPS objects, if we just look at fit 4 here, so we looked at the phases groups data frame, and in addition there are 4 other items within these outputs. obj is the objective functions that can be minimized in order to produce the fit. So if we look at that, you can see that it's a named vector of 3 different objective functions that can be minimized. So ideally, the smaller the value, the better the fit. The next is weighted pure patterns, which is a data frame and it contains the pure patterns of the various reference patterns that contribute to the fit. And in the reference library, in this case, they're all scaled to the same maximum intensity, but here they've been multiplied by the scaling coefficients and adjusted accordingly. So if you add all of these scaled reference patterns up, you get the fitted pattern. And those coefficients that are used to weight the pure patterns are then in this coefficients vector, which can be viewed here. So it's just the names of the coefficients. So the corundum reference pattern is multiplied by 0.075 in order to get it to reproduce the corundum peaks within the sample, and so on. And we'll actually be moving on in later tutorials to visualize these fits, which is probably the most useful way of interpreting whether they are fit for purpose.